September 15th, 2017. A spacecraft the size of a school bus is falling into Saturn's atmosphere at 111,000 kilometers per hour. It has 91 seconds left to live, and in those final seconds, it is still doing its job, still measuring, still transmitting, still sending data home across nearly 1 billion miles of space. What came back in that last signal wasn't aliens. It wasn't a message. It was something stranger than either of those things. Measurements that directly contradicted 30 years of scientific models about how Saturn works. One of the senior scientists on the mission later put it in a peer-reviewed paper in the journal Science, in language scientists almost never use so plainly. The findings were difficult to reconcile with any known process. Sit with that phrase for a second. Not surprising, not unexpected. Difficult to reconcile with any known process, from a researcher who had spent decades studying this planet. This video is about what Cassini actually found, in its final orbits, in its final 91 seconds, and in the years of data analysis that followed its death. No invented patterns, no cover-ups. The real, documented, peer-reviewed story. And it isn't finished yet. Subscribe and hit the bell before this video ends, because the last chapter of this mission is still being written, 7 years after the spacecraft itself burned up. To understand why Cassini's final data caught everyone off guard, you need to understand how much confidence scientists had going into those last orbits. Cassini arrived at Saturn in July 2004, after a 7-year journey from Earth. Over the next 13 years, it completed 294 orbits of the planet, flew past its giant moon Titan 127 times, made 23 close flybys of the small moon Enceladus, and sent home more than 450,000 images along with an enormous volume of scientific data. By any measure, it was one of the most productive planetary missions in the history of space exploration. By 2017, when mission planners made the decision to deliberately end it, plunging the spacecraft into Saturn's atmosphere to guarantee it could never accidentally crash into one of Saturn's potentially life-bearing moons and contaminate it. Scientists believed they had a reasonably complete picture of the Saturn system. They knew about the hexagonal storm sitting at Saturn's north pole, a persistent, six-sided atmospheric feature roughly 30,000 kilometers across, first photographed by Voyager back in 1980 and still rotating, unchanged, when Cassini arrived 24 years later. They knew the intricate structure of Saturn's rings, the named bands, the gaps carved by gravitational interactions with nearby moons, the wave patterns rippling through the ring material like ripples across a pond. And they knew about the water geysers erupting from cracks at the southern pole of Enceladus, a discovery Cassini itself had made back in 2005, a finding that had already reshaped where scientists thought life might be possible in the solar system. What nobody knew was what was happening in the narrow gap between Saturn's innermost ring and the top of its atmosphere, a region roughly 2,000 kilometers wide. That sounds enormous, but compared to the scale of Saturn itself, it's almost nothing. No spacecraft had ever flown directly through it. It was assumed to be filled with small ring particles, potentially dangerous to anything moving through it at orbital speed, and the original mission plan had kept Cassini well clear of it for its entire 13 years of operation. In its final phase, fittingly called the grand finale, mission controllers took a calculated risk and sent Cassini through that gap. 22 times, between April and September 2017, the spacecraft dove between the rings and the atmosphere. And what its instruments found there was not what anyone expected. Before those grand finale dives began, mission scientists ran detailed models predicting what the ring-atmosphere gap probably contained. Every model agreed on the broad picture, a region fairly dense with small particles, shed debris from the inner rings, charged dust grains, material that would need to be carefully navigated to protect Cassini's instruments. Out of caution, engineers oriented the spacecraft with its high-gain antenna facing forward during the first crossing, using the dish itself as a shield against anticipated impacts. When the data came back, the particle count was dramatically lower than expected. The gap was cleaner than any model had predicted. That wasn't a minor discrepancy. The models had forecast particle densities dense enough to be genuinely hazardous, and the real measurements showed something surprisingly clear instead. Practically, this meant the gap could be used more freely than planned, which is exactly why mission controllers felt confident sending Cassini through it 22 separate times instead of a handful of cautious passes. Scientifically, though, it meant something more unsettling. The models describing the inner edge of Saturn's ring system were wrong in a fundamental way. Something was actively keeping that gap cleaner than the physics predicted. Some process removing or preventing the buildup of particles in a region where they should have been accumulating. That process still hasn't been fully identified. Several explanations have been proposed, including electromagnetic effects tied to Saturn's magnetic field sweeping charged particles out of the region. But what's actually maintaining the gap's cleanliness against the constant inward drift of ring material remains, to this day, an open question. The second surprise was stranger, and it's the one behind that difficult to reconcile with any known process, quote. As Cassini made its grand finale passes its ion and neutral mass spectrometer, an instrument built to identify the chemical makeup of whatever gas or particles the spacecraft flew through, was sampling the thin material drifting in that gap, and it found things that didn't belong there. The instrument detected complex organic molecules, not just simple hydrocarbons like methane, but larger, more structurally complicated compounds, with molecular masses high enough to suggest chemistry that doesn't easily assemble in the environment where it was found. Building organic compounds this complex requires specific conditions. Particular temperatures, particular pressures, specific radiation environments, and precursor molecules reacting together over long stretches of time. The gap between Saturn's rings and its atmosphere does not obviously provide any of that. The temperature there is extremely cold. The pressure is close to vacuum. And the radiation from Saturn's powerful magnetic field is intense enough to destroy complex molecules, not build them. Finding sophisticated organic chemistry in that environment is a bit like finding an intricate piece of machinery sitting in the middle of a desert with no roads and no tracks leading to it. The object is there. How it got there, or how it assembled in place, isn't obvious at all. Hunter Waite, the principal investigator for that mass spectrometer instrument and a senior research scientist at the Southwest Research Institute, described the findings with open astonishment. The material raining down from the rings into Saturn's atmosphere wasn't the simple water ice everyone had assumed. It was a complex cocktail. Water, yes, but also organic compounds, fine silica particles, and other materials suggesting the rings themselves are chemically active in ways nobody had previously understood. Scientists proposed that some of these organics might be forming through photochemistry, sunlight-driven reactions acting on simpler molecules over long timescales. But the sheer complexity of what Cassini actually measured exceeded what those models could produce. The gap between what the chemistry models predicted and what the instrument recorded is real, documented, published in peer-reviewed literature, and still not fully resolved. There was also the matter of silica. Fine-grained silica nanoparticles, the same basic material found in certain terrestrial rocks and sand, turned up in the ring atmosphere gap too, hinting at erosion processes grinding ring material down to the nanoscale through countless small impacts. But the distribution and abundance of that silica didn't match what the erosion models predicted either, adding one more unexplained layer to the chemical inventory. This whole phenomenon, material flowing from the rings down into Saturn's upper atmosphere, is called ring rain, a term coined years before Cassini measured it directly, based only on indirect evidence. What Cassini's grand finale orbits confirmed is that ring rain is heavier, more chemically complex, and more variable across latitude than any earlier model had described. The third surprise came from Saturn's magnetic field, and this one reaches far beyond ring chemistry into fundamental questions about how planets generate magnetic fields in the first place. Every planet in our solar system with a significant magnetic field, Earth, Jupiter, Saturn, Uranus, Neptune, generates that field through the motion of electrically conducting fluid deep in its interior. On Earth, that's the molten outer core, mostly liquid iron, churning in patterns driven by heat flow and the planet's rotation. On the gas giants, it's electrically conducting fluid hydrogen. ordinary hydrogen compressed under such extreme pressure that it behaves like a metal, conducting electricity and generating a magnetic field through its motion. A basic feature of any field generated this way is that its axis, the line connecting the magnetic north and south poles, should sit at some tilt relative to the planet's actual rotation axis. Earth's magnetic poles are currently offset from its geographic poles by about 11 degrees. Jupiter's tilt is roughly 10 degrees. Uranus and Neptune are far more dramatic, tilted more than 50 degrees from their rotation axes. Saturn breaks the pattern entirely. Its magnetic field is aligned with its rotation axis to a degree of precision the scientists who measured it have called extraordinary. Before Cassini's final orbits, the alignment was already known to be unusually close, within about 1 degree, which was already puzzling enough to drive theoretical work asking why Saturn behaved so differently from every other planet. Then came the grand finale measurements, taken as Cassini dove repeatedly through the region where Saturn's magnetic field is strongest, producing the most precise measurement of that field's alignment ever made. The result was almost hard to believe. The tilt of Saturn's magnetic field relative to its rotation axis came out at less than 0.0095 degrees, not even 1/100th of a degree. Michele Doherty, principal investigator for Cassini's magnetometer at Imperial College London, described the finding in her published research as posing a fundamental challenge to every existing model of how planetary magnetic fields form. Here's why that's such a problem. The standard theoretical framework, called magnetohydrodynamics, describes how conducting fluids generate magnetic fields through motion, and it includes a mathematical result called Cowling's theorem, which states that a perfectly symmetrical, perfectly aligned magnetic field cannot be sustained by fluid dynamo action. Something has to break the symmetry. Something has to tilt the field, at least slightly, away from the rotation axis. Saturn's field appears to defy that constraint. It isn't perfectly aligned. The measurement carries some uncertainty, and there are likely small asymmetries current instruments simply can't resolve. But it's so close to perfect that explaining it requires proposing mechanisms with no confirmed precedent anywhere else in planetary science. One hypothesis involves a layer of electrically conducting fluid at an intermediate depth inside Saturn, suppressing the tilt through a specific kind of helical convection. Another suggests differential rotation, layers of the planet spinning at slightly different speeds, smoothing the asymmetries out. Neither hypothesis has been confirmed. As of 2026, why Saturn's magnetic field is so precisely aligned with its rotation axis remains one of the genuinely open problems in planetary science. None of these findings were anticipated. All of them came from clean, well-calibrated instruments on a spacecraft that performed exactly as designed, right up until the moment it hit Saturn's atmosphere. But the single most extraordinary discovery associated with this mission doesn't come from its final orbits at all. It comes from a completely different object Cassini studied years earlier, and from what a different telescope confirmed about it 6 years after Cassini was gone. Enceladus is Saturn's sixth largest moon, roughly 500 kilometers across, covered almost entirely in fresh, bright ice that makes it one of the most reflective objects in the entire solar system. In 2005, Cassini discovered that Enceladus has an active geological process happening at its south pole, a set of long, parallel cracks in the icy surface, nicknamed tiger stripes, from which enormous plumes of water, vapor, and ice particles erupt continuously into space, feeding material into Saturn's faint E-ring. This discovery was immediately extraordinary. An active, geologically driven process on a moon this small requires an internal heat source, because Enceladus is far too small and too distant from the sun to be warmed meaningfully by sunlight. The heat driving those plumes comes from tidal flexing, the gravitational tug-of-war between Enceladus, Saturn, and other nearby moons like Dione, which rhythmically squeezes and stretches the moon's interior, generating heat through friction. That heat is enough to sustain a liquid water ocean beneath the ice shell, with the tiger stripes acting as the connection between that hidden ocean and open space. A liquid water ocean in a body sitting far outside the sun's habitable zone. A discovery that quietly rewrote where in the solar system scientists thought life could plausibly exist. Cassini went on to fly through those plumes many more times, analyzing their chemistry in detail. It found water ice. It found simple organic compounds. And it found molecular hydrogen, a detail that mattered enormously, because molecular hydrogen in the plumes is a strong sign that hydrothermal reactions are happening on the ocean floor, where hot water from the rocky core reacts with minerals in a process called serpentinization. On Earth, hydrothermal vents on the seafloor support entire ecosystems that live completely independent of sunlight. Finding evidence of the same basic process in Enceladus's ocean was one of the most significant astrobiology findings in the history of space exploration. By the time Cassini's mission ended in 2017, the chemical inventory of Enceladus's plumes included water, molecular hydrogen, carbon dioxide, methane, and a range of other organic compounds. Scientists realized that 5 of the 6 elements considered essential for life as we understand it — carbon, hydrogen, nitrogen, oxygen, and sulfur — had all been confirmed in the plume material. One was missing: phosphorus. Phosphorus isn't a minor detail in the chemistry of life. It's a core structural component of DNA and RNA, the molecules that carry genetic information in every known living organism. It's the backbone of ATP, the molecule cells use to store and transfer energy. Without phosphorus, life as we understand it simply doesn't work. Finding it in Enceladus's ocean would complete the inventory of every element life requires and remove the last chemical objection to the idea that this ocean could, in principle, support living chemistry. Cassini itself never confirmed phosphorus in the plumes. Its mass spectrometer wasn't sensitive enough to detect phosphorus compounds at the concentrations actually present during its flybys. The answer came 6 years later, from a different direction entirely. In June 2023, Frank Postberg, a planetary scientist at the Free University of Berlin who had spent years working with Cassini's archived mass spectrometry data, led a team back into that archive. This time with improved analytical techniques and a far more complete understanding of how the instrument responded to specific compounds. In ice grains Cassini had captured from Enceladus's plumes years earlier, data that had been sitting in an archive the entire time. The team found phosphorus, not just traces. Concentrations of phosphate compounds orders of magnitude higher than those found in Earth's oceans, sitting in the same water that's already chemically active, hydrothermally heated, and known to contain every other essential ingredient. The paper was published in Nature in June 2023, and Postberg's team described the finding as completing the inventory of the key elements necessary for life as we understand it, right there in Enceladus's ocean. The James Webb Space Telescope has since independently confirmed and extended parts of this picture, observing that Enceladus's plume activity is even larger than Cassini ever measured. The water vapor forms a vast cloud spanning the entire E-ring, more extensive than anything Cassini fully mapped during its mission. Cassini found the ocean. Cassini found the heat. Cassini found 5 of the 6 essential elements. And years later, scientists went back into Cassini's own archived data and found the 6th. The ocean beneath Enceladus's ice now has a confirmed chemical inventory satisfying every known prerequisite for life as we understand it. Whether life is actually there is still completely unknown. No observation confirms biological activity, and having the right ingredients doesn't guarantee they've assembled into anything living. But the distance between "we don't know if the ingredients are present" and "we don't know if the chemistry has become life," that's the entire scientific journey from Cassini's 2005 plume discovery to Postberg's 2023 phosphorus paper. Cassini didn't find life. It did something more rigorous and more durable than any single life detection claim could ever be. It systematically established the physical and chemical conditions that make life possible in a place nobody had any reason to look before 2005. Step back from Enceladus for a moment, because the full Cassini story isn't only about that one moon or the ring gap chemistry. It's also about how little we truly understood a planet visible to the naked eye. One humans have watched since long before the invention of the telescope, and one we had a dedicated spacecraft orbiting for 13 straight years. Saturn radiates significantly more energy than it receives from the Sun. That isn't unique to Saturn. Jupiter does the same thing, but the underlying mechanism isn't fully understood for either planet. On Jupiter, the excess heat is thought to be primordial, released slowly as the planet contracts under its own gravity, a process ongoing since its formation. That explanation doesn't work as cleanly for Saturn, because Saturn is smaller and should have radiated away its primordial heat much faster. Several alternative mechanisms have been proposed, including the slow separation of helium from hydrogen deep in Saturn's interior, a process nicknamed helium rain, where droplets of helium sink through the surrounding hydrogen, releasing gravitational energy as heat along the way. But the models built around this process don't quantitatively reproduce the excess heat Cassini actually measured, at the level of precision the data demands. Saturn's atmosphere kept surprising scientists throughout the mission, too. The hexagonal polar storm, studied by instruments that didn't even exist when Voyager first photographed it in 1980, turns out to be far more than a static hexagonal outline. It contains jet streams, wave structures, and embedded vortices interacting in ways that current atmospheric fluid dynamics models struggle to fully reproduce. Why a planetary atmosphere sustains a persistent hexagonal shape at all, rather than the circular or oval patterns seen elsewhere, remains an active area of research. A massive storm that erupted in Saturn's northern hemisphere in 2010 and 2011. The largest and most intense storm observed on any planet since the Voyager era, circled the entire planet within months, and Cassini tracked its evolution in a level of detail impossible from Earth. As the storm mixed material up from deep in the atmosphere to much higher altitudes, the data revealed chemical signatures, particularly involving water and phosphine, that were difficult to explain using the standard models of Saturn's atmospheric chemistry. Phosphine on Saturn is its own puzzle. When phosphine was detected in Venus's atmosphere in 2020, it sparked enormous scientific controversy as a potential biosignature. On Saturn, phosphine has been known to exist for far longer, and its abundance in the upper atmosphere has remained a standing mystery, because the compound should be destroyed by ultraviolet radiation faster than it could plausibly be resupplied from lower in the atmosphere. Unless resupply is more efficient than current models suggest, or the destruction process is slower than calculated, or there's some production mechanism in the atmosphere that hasn't been identified at all. None of those possibilities has been resolved. All of them remain open, and all of them are being actively worked on using Cassini's archived data. The real, documented, peer-reviewed story of Cassini's final moments contains no alien signals, no hidden encrypted messages, no cover-up. What it contains is something arguably more profound, a systematic demonstration that a planet humans have studied for 4 centuries still has fundamental properties we don't understand. It contains the discovery of a moon with an ocean holding every chemical ingredient life requires. It contains a ring system that's more chemically complex and dynamically active than any model predicted. And it contains a magnetic field puzzle that challenges the theoretical framework scientists use to explain how every other planet in the solar system generates its own field. These aren't comfortable findings. They're not the kind that let researchers say, "We understand that now," and move on. They're findings that expand the questions rather than closing them. Findings that leave Saturn more mysterious, not less, after 13 years of the most detailed observation any spacecraft has ever managed in the outer solar system. On September 15th, 2017, at 7:55 a.m. Eastern Time, Cassini's signal was lost as the spacecraft entered Saturn's atmosphere at 111,000 kilometers per hour. The team at NASA's Jet Propulsion Laboratory watched the signal strength hold steady until atmospheric drag finally overwhelmed the spacecraft's ability to keep its antenna pointed at Earth, and then it simply stopped. Engineers and scientists who had spent years of their careers on this mission were openly emotional. Some cried. 13 years of relationship with a distant system had ended in 91 seconds of final transmission before the spacecraft carrying the instruments was vaporized in the atmosphere it had spent so long studying. But the data it sent home over those 13 years, including the grand finale measurements still being analyzed today, didn't stop being scientifically productive when the signal ended. Cassini's mission ended in September 2017. Its science didn't. The phosphorus discovery came in 2023. Papers on ring chemistry are still being published. The magnetic field alignment puzzle remains open. Enceladus's ocean is still one of the most actively studied subjects in astrobiology. And the James Webb Space Telescope, which began science operations in 2022, has added new observations of the Saturn system that extend what Cassini measured, including images of that vast hydrogen cloud around Enceladus, reaching far beyond anything Cassini itself ever mapped. When Postberg's team found phosphorus in Cassini's archived data in 2023, they were using instruments and analysis techniques that didn't exist during the mission's active years. That's one of the most important things about space mission data in general. The raw numbers sit in an archive, and as our tools for interpreting them improve, that archive keeps yielding findings the original instruments were quietly collecting all along, findings nobody was equipped to see at the time. There is almost certainly more still sitting in the Cassini archive. The only open question is what new questions need to be asked and what new tools need to be built to find it. The next mission to Saturn's system is still in the planning phase. Several concepts have been proposed and studied, and the most advanced is a dedicated return to Enceladus specifically. A mission built to fly through the plumes with instruments capable of looking directly for signs of life, rather than just the chemical conditions that make life possible. Such a mission would carry mass spectrometers an order of magnitude more sensitive than Cassini's, capable of detecting amino acids, lipids, and other complex biological molecules if they're present in the plume material. As of 2026, that mission hasn't been selected or funded. But the scientific case for it has been building for years, and that case rests entirely on what Cassini found. The ocean is there. The heat is there. The chemistry is there. The only question the instruments we've sent so far can't answer is whether anything is actually living in it. That's the answer a future mission to Enceladus would try to provide. And the foundation for that future mission was laid by a spacecraft that plunged into Saturn's atmosphere on a September morning, transmitting data for 91 seconds as it burned, sending home the final readings of a 13-year conversation between human science and the second largest planet in our solar system. The conversation ended. The questions it left behind have not. If this is the kind of story you come here for, the real, documented, still unfolding science, not the wild guesses floating around online, subscribe and turn on the bell. Tell me in the comments which of these findings surprised you the most, and share this with someone who'd want the real story instead of the rumors. We'll see you in the next one.